Right, let's get this out. Yeah, set this. Okay, D block elements. How much are you familiar with it? What do you know about D block elements till now? सबसे पहले, where do you find D block elements?
The 3rd to the 12th group.
3rd to 12th group, absolutely. So they are in between S and P block requirement. Can just do this. Yeah, there you go. The highlighted ones, these are the D block elements.
Coordination khatam?
I'll take it for you guys. Like last week I started coordination, right? So
Yeah.
next week.
Oh, acha, so this is new chapter starting again. Yeah. So good.
So yeah, D block elements, like the elements that are located in the D block of the periodic table, highlighted groups and periods. Yeah, these come under D block elements. They're also called transition metals. Two reasons. So sabse pehle their name was transition metals because they were involved in the transition between like S block to P block. So predominantly electropositive to predominantly electronegative. Okay. And later on, like when we started studying about it, because they're like the last electron goes in the d orbital, because of the dd transitions, like electrons keep jumping within the d orbital subshells. So they came to be known as transition metals. So the exceptions, like the elements that belong to T block, but those that do not come under transition metals, like this is something I discussed yesterday also, right? So the elements that have completely filled d or like where electrons fill up the d orbital, which is right at the end. Zinc, cadmium, I was right. So zinc, cadmium, and mercury. So these are not transition elements because in May you don't have that typical d electron transition within the d orbital. Like they have completely fully filled d subshell. Okay. Anyway, why they have fully filled subshell? Like we look at the electronic configuration and all in detail. But yeah, so d block elements, electron goes into the d orbital, which is why they are called d block elements. What else? They're also called transition elements. So when it, so the valence electron, like depending on which shell it goes in, you have the 3D, 4D, 5D, and 6D elements. So 6D is like they are predominantly very radioactive. You can barely study them. So a lot of what we are going to be studying about in terms of trends and all, we'll just be looking at 3D, 4D, and 5D. Won't be talking about 6D a lot. Zinc, cadmium, mercury. Yeah, so they have a D10 configuration, so they don't come under transition, but they are D block elements. Similarly, F block also. Lanthanides and actinides. This you had studied, you must be familiar with. The elements that follow lanthanum, they are lanthanides, and elements that follow actinium, they are actinides. Transition के अंदर है, so they are called inner transition elements, F block. And F block elements में the last electron goes into the F orbital. So there's only 2 F orbitals possible so far, which is your 4F and 5F orbitals. Third shell में F नहीं है, you just have up to 3D, and then 4S, 4P, 4D, and then 4F and 5S are the only ones possible. Okay. Now we'll get into the details of it. All right. So we'll stick to D block first, and then we'll look at F block. So D block, pehla thing that we talk about is electronic configuration. Similar to your SP block, same thing. We'll talk about electronic configuration, atomic size, ionic size, ionization enthalpies, oxidation states, same properties. Okay. All right. What is the general electronic configuration for d block elements?
NS to N minus 1 D 1 to 10.
Yeah. So NS can be either 1 or 2.
1 or 2.
So N minus 1 E, this is incomplete, ranges from 1 to 10. And NS, usually, like theoretically, it should be 2 because S is filled first, but there are a couple of anomalies. It 1 to 2, 1 or 2. Okay.
1 or 2.
So one anomaly, the first anomaly that we come across would be chromium. So atomic number is 24. So can you guys figure out the electronic configuration for this?
This is the
Why
copper.
isn't S? Why isn't NS one first?
In the sense,
Energy.
energy level, like order of filling, NS1 pehla hoga, but this is a convention that we follow. Like when we're just talking about the valence shell, 3D comes pehle, right? Like n minus 1D is the inner orbital, NS is in the end. So this is the order that you represented by.
Yeah, but like we fill it first the 4S then 3D, so shouldn't we
Yeah.
write it like that?
Can be written either way, you find both. As long as the correct, this thing contains the correct number of electrons.
How can NS be written back and still be correct?
So that's
Because,
the
because
lot.
of the energy, when the electron is taken, it will be taken from the S.
This is the outermost one. This is the order of the shells in which they exist. The order of filling, like based on the energy, NS is filled first and then N minus 1D is filled next. So always like you have the K shell, N equal to 1 first, then L, N equal to 2, N equal to 3. So this includes 3S, 3P and 3D. Uske baad, bahar you get N equal to 4, right? So the order of shells, yeah, 3D comes before 4S, 4D comes before 5S. The order of filling, S is filled first and then the D is filled after that. Because that depends on the energy balance. Okay. Okay, so chromium up to argon is 18. Uske baad
3S, 4S 1 and 3D 5.
3D 5, yeah. So yahan pe ideally it should be 4s2, but when it has a chance of a half filled orbital, the electron will jump to this for that extra stability. Okay. So similarly, copper, jiska atomic number is 29. This also follows that rule. Argon ke baad 4s1 and then 3d10 because it's got this fully filled shell. Okay. Another thing to remember is, like, if you go back, do you guys remember the formula for the energy levels in an atom? I know this is like really, really far off first chapter in 11th grade, but do you recall it?
Recall what?
The formula for energy level, like first shell का energy कितना है, second shell का energy कितना है, third shell का energy कितना है, होगा? No.
There was a formula for that?
Yeah. 13.6 electron volts, and then the first shell is 13.6 electron volts, and then it varies into n square upon z. No? Okay.
We have not done this formula.
What do you mean? Both,
We have done it.
but that's okay. It was like a really tiny part of the chapter, so it's okay. But one thing that I want you guys to know.
What is that, like electron excitation from ground state and all that?
Yeah, different energy levels, right? When we talk about energy levels, energy ka ek magnitude hoga na, like it has that quantity amount of energy, right? So how do you get that numerical value? Like how is that varying? Uska ek formula hai. But it's okay. So what I want you guys to know at this point is, as you go on to the higher energy levels, the difference between each orbital ka energy level, the difference keeps decreasing. It's not a regular trend. So n equal to 1, n equal to 2 may, like let's say if there is this much of a jump, n equal to 3 is going to be slightly lower. And n equal to 4 is going to be slightly lower than that. And then 5 will be lower than that. Okay. So the consequence of this is that as you start looking at the higher energy levels, there's going to be like the difference between the energy level is not like it keeps decreasing. So there's not so much of a difference between the energy values. So this factor is, when we're talking about the smaller elements like sodium, potassium, chlorine, and all that, like this doesn't come into picture because maximum like third shell tak hi hai unka. But as you keep going, which involves like your D block and F block elements, especially the F block elements, the electron can jump between the energy levels quite easily. So there, along with the energy values, even your electronic repulsions within the same shells like starts coming into the picture. Okay. So I'll talk about the specific cases as we come across it, like the exceptions and anomalies and all. But I want you guys to remember this factor, like the energy, like the difference in the energy values. As you go to the higher energy levels, like n equal to 4, n equal to 5, n equal to 6, the higher values the difference is not a lot. Like it doesn't take so much for an electron to jump the energy values. Okay, so just keep this in mind. That's partially the reason why this is easily possible. Like 4s say it can just go on to 3D because this extra stability is worth that difference in energy level, even though 3D is at a higher level compared to 4s. Okay, so these are like some of the exceptions. We have chromium, copper. This is in 3D series only. Even in like 4D and 5D series, you'll find it. In fact, 4D and 5D you'll find a lot more cases. So it's not specifically only the half filled, fully filled, but even if it is like incomplete, you'll find S1 configurations there. So let me, 1 minute. Yeah, there's a table here all in one way. So all the electronic configurations are given there. I'll just show it to you. So you can see here, first series, this is pretty much what you expect it to be. So except for chromium and copper, or kisi mein you don't find that anomaly. How do I make this go away? Yeah, so only in chromium you have a 4s1 3d5, copper may you have a 4s1 3d5. But when it comes to the higher order, higher elements, like a bigger elements, 5s may you find that all of these are taking S1 configuration, even though you're not getting a proper complete half filled this thing. Okay. This is again like copper ke baad silver is the same reason. You have D10 fully filled, more stability. But in this case, you can see that like these are taking S1 configuration because 5s 4D may the difference in energy values is not so much. Also, 5s and 4D is made like 4D orbitals are big enough that these electrons, even though they all occupy the d orbitals only, they'll face lesser electronic repulsions. So it's just easier that way. Okay. Third series, at this point, you're getting into s orbital. So again, like 6s2, and then 5d may thoda sa, like again, once the 4f is filled out, you get 1, 2, 3, 4, 5, 6, 7. Follows the regular thing. Okay, so I wanted to highlight this because just make note, it's not just chromium and copper and the things below it, molybdenum, silver, that are the exceptions. You have a few others as well, niobium, technetium, ruthenium, these also. So that's why we say general electronic configuration, n minus 1 s either 1 or 2, and then nd can be variable 1 to 10. Okay. So this is about the electronic configuration. Okay. Another like consequences of electronic configuration. So D block elements, because 4s either 1 or 2m, maximum like most of the all of the elements except for 1 or 2 of them show +2 oxidation state. So this is where they lose the s electrons. So after +2, the rest of it is all like variable. It depends from element to element. But this is like a common thing among all D block elements that they show a +2 oxidation state. This is the most common oxidation state where the outermost s electrons are lost, +2.
Wait, can you repeat the s electrons lost part?
So if it has to form ionic compounds by losing electrons, it will lose the outermost shell में जो भी electrons है ना. So that is the reason, like outermost shell matlab n equal to 4 is the outermost shell that they have. So these s electrons are the ones that are lost.
But isn't S before, like S पहले आता है ना, then D?
Filling order में s पहले आता है, but existing you always have n equal to 1, n equal to 2, n equal to 3.
अच्छा, oh.
The outermost electrons are always removed first, like you go from outside to inside.
But like in electronic configuration, what do we write? Filling order or n order?
Anything, like go with filling order. That's more intuitive and easier when you're writing the electronic configuration. But don't be rigid, don't just stick to it. Have an understanding of what shells are, what comes where. Outermost jo bhi hai, those electrons will be removed. So in this case, the 4s electrons are always removed first. Okay. So +2 oxidation state is the most common one. All the D block elements have a +2. So beyond that, like copper exhibits a +1 oxidation state. When the D electrons are lost, like iron has a +3 as well. All the other comes like they're specific to that particular element, but +2 is common to all. Yeah. So when the D block element form ions, so all the ions with a given DN configuration will have they'll have similar magnetic and electric, like similar properties. So we'll show similar magnetic and electronic properties. Okay. Because their electronic configurations are the same, their magnetic moments will be the same. Like what this means is, for example, if you have Fe 2 plus and cobalt 3 plus. So both have both end up with D6 configuration. So the magnetic moments, anything related to their like electronic configuration, like transition of electrons and all of that will be similar. Okay. Yeah. What else do we have? And also, like, because of their electronic configuration, because of vacant d orbitals, half-filled d orbitals, this is the reason for all the other characteristic properties, which are variable oxidation states, the fact that like complex ion formation, the things that are very specific to d block elements. Colored compounds, catalytic properties. Like if you notice, a lot of D block elements we use as catalysts: nickel, iron, vanadium, compounds of theirs, all of that. Like the reason for all of this is their electronic configuration. If you had to be more specific, it's the fact that they have incomplete d orbitals or half-filled d orbitals.
What do you mean by variable oxidation states? Like they have different
Yeah.
oxidation states.
Yeah.
But
So
plus 2 is the common one.
yes. Like iron has +2 and +3. Copper has +1 and +2. If you go with manganese, it has like the maximum amount. After +2, it has +1, then +3, +5, +7, all of it. Chromium has +2, +4, +6. So the reason why it's capable of exhibiting all those different oxidation states, all these elements, is because of incomplete like the d orbitals, the d orbital electrons, which are like unpaired, are also capable of forming chemical bonds, chemical compounds. An example is complex ion formation. Apart from that, with halides and oxygen also, they form like higher oxidation state compounds with like potassium dichromate, if you remember, potassium permanganate, Mn2O7, all these compounds. Okay. Let me know when you guys have finished noting. This is all about electronic configuration.
Miss, what did you say about catalytic
Yeah.
properties?
So D block elements are used as catalysts in a lot of reactions, like nickel, palladium, platinum used in hydrogenation. This is something you're familiar with. Similarly, iron is also used, I think, in Haber's process. Yeah. Production of ammonia takes place over iron.
Yeah, Fe.
And vanadium, like not just pure metals, but metal K compounds, like vanadium pentoxide is used as a catalyst in the manufacture of sulfuric acid.
V2O5, right?
Yeah.
Contact process.
Yes. So all these are D block elements. So what happens is, so they are like, because of the empty d orbitals, they are capable of forming coordinate bonds complexes. Sometimes these intermediates happen to be high energy and unstable, so it kind of like forms and doesn't form. But for the primary reaction with which it forms these bonds, it's like an alternate energy group, like takes place more easily.
And And what did you say about D block elements having variable oxidation state? You said something about unpaired electrons also form.
So because they
Some-
have unpaired electrons and vacant orbitals,
Yeah.
so these electrons are available for forming chemical bonds.
Form complex compounds, right? You
Complex
said.
compounds is one case, but otherwise also like any sort of chemical bonds.
Thank
Sorry,
you.
what did you say about chemical bonds? I couldn't.
No, the unpaired electrons, vacant d orbitals are available to form chemical bonds. So it could be ionic, could be covalent, could be like a coordinate compound for complex compounds. जो भी हो. They're,
Does
they,
it mean they
they're
are like highly reactive or?
doesn't have like reactivity will depend on the individual element. It depends on the energy values, like as we saw in the thermodynamics ke chapter, it depends on
So
the
reactivity doesn't depend on the number of orbitals or the number of unpaired electrons in those orbitals.
not really one of the cases, but it's not the factor, and it's not even like a major factor. It also depends on hydration, ionization energy, size of the atom, and like a lot of other things also come into the picture. So you can't like predict the reactivity purely based on the number of electrons. Okay. All right. So we'll quickly look at the physical properties. What's the first thing that comes to mind when you think of D block elements? I'll show the periodic table here. Yeah.
Metals.
Metals, yes. So they are all metals with very typical metallic properties. Do you guys remember? Tell me some of these metallic properties.
Malleable,
Form based.
Malleable,
sonorous, lustrous.
lustrous, ductility, all of this, conductivity. Yeah. So D block elements, they are typical metals. They show extremely typical metallic properties. So they are also characterized by very high melting point and boiling points. Actually, we'll not talk about boiling point as boiling point. So this relates to enthalpy of atomization. High melting point and let's say high enthalpy of atomization. What else?
What is atomization?
Yeah. So melting point and enthalpy of atomization, there's a little more we'll get into it. So we'll talk about the trends of the melting point also across a period. Other properties you can talk about, they're very hard, not volatile. What else do we have? Of course, exceptions to this very hardness are zinc, mercury, cadmium, like the ones with completely filled this thing. Then high melting point, atomization. Yeah. And another point, this we haven't discussed about this pehle, but Smera might be a little like familiar with this. These metals, they show or they have more than one typical metallic like crystal structure. Okay, the meeting might come to an end anytime now, so just be prepared. So I'll discuss these three in detail. The next thing when we reach that, the reason behind it and the trends and all that. Yeah. All right. So metallic structure, matlab, we're talking about the crystal lattice. Have you guys heard of this before? Lattice. We've come across it, lattice energy and all.
Yeah, para products are more symmetrical, so they're well fitted in the crystal lattice.
So what do you think a lattice means?